Welcome back to The Explainer. Listen, I want you to picture the most advanced, ultra-efficient, just absolutely tireless engine ever created. No gas, no electricity, no assembly line. It's actually beating right inside your chest right now. The human cardiovascular system is just a total marvel of biological engineering. So today, we're popping the hood. We're going to look at exactly how the heart, the wiring, and this massive plumbing network all work together to keep you going. Let's dive right in.
Here's our blueprint for the explainer. We're kicking things off with the ultimate engine itself. Then we'll map out the electrical grid, trace that crazy plumbing network, dive into how it stays under pressure, and finally look at the two distinct circuits running the whole show.
All right, Section 1, the ultimate engine. We're talking about the sheer scale of the heart's daily workload here. Just take a look at this number, 5 to 6 liters. You're just sitting there, right? But even at a totally normal resting heart rate, your heart is pumping your body's entire blood volume, yeah, that's 5 to 6 liters, every single minute. I mean, literally every drop of blood in your body is making a full round trip through this engine in just 60 seconds. It's wild.
So how exactly does it pull that off? Well, medically speaking, we call this your cardiac output. And it's actually a pretty simple calculation. Just multiply your heart rate by your stroke volume. Now, stroke volume is just the actual amount of blood ejected with a single beat, which sits right around 60 to 80 milliliters. So you multiply that single squeeze by an average of, say, 75 beats per minute, and boom, you hit that massive 5-liter milestone. To hit that stroke volume, the engine runs on this perfect rhythmic cycle of pumping and resting. You've got systole, which is the active contraction and emptying phase, and then diastole, that absolutely crucial relaxation and filling phase. You know that classic lub-dub sound you hear through a stethoscope? You might think that's the heart muscles flexing, but no, actually, scratch that. It's just the internal valve slamming shut. The lub is the atrioventricular valves closing during systole, and that dub is the semilunar valve snapping shut right after. Okay, let's actually trace the path of the fuel here, starting on the right side of the pump. Deoxygenated blood returns from your body and drops into the top chamber, the right atrium. Then it flows down through the tricuspid valve right into the right ventricle. From there, it gets pumped straight to the lungs to grab a fresh supply of oxygen. You can basically think of the right side of your heart as the dedicated lung pump. Once that blood is all freshly oxygenated, it loops back to the left side, entering the left atrium. It drops through the mitral valve into the left ventricle, and then, wham, it blasts it out to the entire body. Now, here's the really cool part. Both ventricles pump the exact same amount of blood, but the left ventricle's muscular walls are actually about 5 times thicker than the right. Why? Because it has to forcefully push that blood all the way from your chest down to your literal toes. Of course, a mechanical pump is totally useless if nothing tells it when to fire. So moving on to Section 2, the electrical grid. Time to look at how we wire the heart.
See, your heart actually generates its own electrical impulses. The main spark plug here is the SA node sitting up in the right atrium. Left completely to its own devices, it wants to fire about 100 times a minute, though your nervous system kind of chills it out to about 75 when you're resting. But look at the brilliant backup systems built into this thing. If the SA node fails, no panic, the AV node takes over as a backup pacemaker at 40 to 60 beats a minute. If that goes down, the bundle of his steps in at 20 to 35 beats. The whole system is literally engineered to keep you alive no matter what.
And this really shows how smart the engine is when it needs to rev up. Ever wonder why your heart pounds so hard when you're on a run? It's called Starling's law of the heart. When you exercise, your moving muscles send more blood rushing back to the heart. All that extra volume physically stretches out the heart muscle walls. And in response, the muscle naturally contracts with way more force, automatically increasing your stroke volume. So without you even consciously thinking about it, your heart can crank its output up to 4 times its resting level just by being stretched.
All right, so we've got the pump, we've got the electrical grid, now we've got to move the fuel. Welcome to Section 3, the plumbing network. We're talking arteries, veins, and capillaries.
Now, arteries and veins have totally different jobs, and their designs match perfectly. Arteries carry blood away from the heart. These are your thick-walled, super high-pressure, outbound pipes lined with smooth muscle to tightly regulate flow. Veins, on the flip side, bring blood back. They're much thinner, much lower pressure, inbound pipes. But because they run at such a low pressure, they face a pretty massive physical hurdle. Seriously, think about this for a second. If veins are low pressure, how on earth does blood from your feet make it all the way back up to your chest, constantly fighting against the relentless pull of gravity? The engineering fix here is just genius. We've got three main mechanisms. First up, your skeletal muscles literally moonlight as secondary pumps. Every time you take a step, your leg muscles squeeze those deep veins. Second, the veins have these tiny one-way valves built in, kind of like trapdoors. They let the blood get pushed up, but instantly snap shut so it can't fall back down. And third, simply taking a breath pushes your diaphragm down, which compresses your abdominal veins and physically forces the blood upward. It's brilliant. But moving all this fluid requires some seriously precise calibration, which brings us to Section 4, under pressure. Let's talk about regulating the flow. You know the numbers. A normal systemic arterial pressure averages around 120/80 millimeters of mercury, but that high pressure has to drop off a cliff as it moves through the system. By the time the blood actually reaches your capillaries, the pressure has to be incredibly low. Why? Well, capillary walls are literally only one cell thick. They have to be extremely fragile to let oxygen, nutrients, and waste diffuse in and out of the tissues easily. If that high arterial pressure hit them directly, it would completely blow out the pipes.
But what if the pressure drops too low everywhere, like from severe dehydration? Well, your body has a chemical backup plan. Your kidneys are constantly acting as flow monitors. If they sense a dangerous pressure drop, they secrete an enzyme called renin. This kicks off this whole complex chain reaction, the renin-angiotensin-aldosterone mechanism, which basically clamps down on blood vessels and tells your body to hoard water. That forces your blood pressure safely right back up.
And the kidneys are definitely not flying solo here. Hormones are constantly fine-tuning this engine. Epinephrine from your adrenal glands cranks up your heart rate and systolic pressure when you're stressed. Antidiuretic hormone, or ADH, tells your kidneys to hold on to water to boost the overall volume. But honestly, my absolute favorite is atrial natriuretic peptide, or ANP. If your blood pressure gets too high, it physically stretches the walls of the heart's atria. The heart then secretes ANP itself, telling the kidneys to just dump sodium in water, which drops your pressure. The heart is literally prescribing its own medicine to keep from overworking. How cool is that? All right, we've mapped the parts, the wiring, the pressure. Let's bring the whole thing together in Section 5, the two circuits, looking at the pulmonary and systemic loops. Your cardiovascular system is essentially a massive double loop. You've got the pulmonary circuit, which is the loop from the right ventricle to the lungs and back. That absolutely has to stay low pressure so fluid doesn't leak into the tiny air sacs of your lungs, because that would cause pulmonary edema, which is bad news. Then you have the systemic circuit. That's the heavy-duty loop from your left ventricle out to every single tissue in your body, and it needs a lot of high pressure just to overcome all that resistance and gravity. And within that massive systemic circuit, you've got some pretty fascinating subroutes. Take the hepatic portal circulation. Instead of blood just flowing straight from your digestive organs back to your heart, it takes a little detour through the portal vein into your liver. Your liver acts like this incredibly advanced inline chemical filter. It regulates glucose, balances amino acids, and scrubs out potential toxins, like alcohol or medications, before that blood is ever allowed to join the main circulation. And that brings us to a final thought. We've looked at the sheer brute power of the muscular pump, the precision of the backup electrical grids, the absolute genius of those little one-way valves, and the crazy chemical balancing act keeping our blood pressure in check. Your heart beats about 100,000 times a day, every single day, without you ever once asking it to. It's incredibly resilient, but it's also immensely complex. So the question I want to leave you with today is this. Knowing just how tightly integrated all these systems are, what happens when just one tiny part of this delicate 100,000 beat a day machine falls out of rhythm? The ways modern medicine can step in to fix those precise misfires? Well, that's a whole other explainer. Thanks so much for joining me today, and keep learning.